You know, in our digital world, we've always had this fundamental conflict. To use our data, we have to expose it. But what if that just wasn't true anymore? Today, we're going to look at a technology that many have called the holy grail of cryptography, one that promises to solve this conflict once and for all. It's called fully homomorphic encryption, and it might just change everything we think we know about data privacy.
So here's the central paradox, right? We're really good at encrypting our data when it's just sitting on a hard drive. That's data at rest. And we encrypt it when we send it over the internet. That's data in transit. But the second a cloud server needs to actually do something with it, run an analysis, train an AI model, all that protection just has to come off. And that is the moment of maximum vulnerability. And this exact vulnerability, it's got a name, the decryption gap. It's really the Achilles heel of all our traditional privacy models. Because for that brief moment in time, your most sensitive information is sitting in the clear on someone else's computer. It's only protected by company policies, not by the rock-solid laws of math. This is the exact problem that fully homomorphic encryption, or FHE, was built from the ground up to solve. Okay, so this all leads to a question that sounds like something straight out of science fiction. What if a server could perform any calculation you wanted it to on your data while that data stayed completely encrypted and totally unreadable the entire time? That is the incredible promise of FHE. And to get our heads around how that's even possible, let's use a simple but really powerful analogy. All right, let's try this out. Imagine Alice is a jeweler. She has some raw diamonds and gold. That's her data. She puts them inside a special lockbox, and only she has the key. She then sends this locked box to Bob, a skilled artisan, who is our cloud server. Now here's the clever part. The box has these sealed gloves built right into the sides. Bob can put his hands into the gloves and, following Alice's instructions, assemble a beautiful necklace inside the box. He can work with the materials, but he can never actually see or touch or steal them. When he's done, he just sends the locked box back. Alice uses her key, opens it up, and there it is, the finished necklace, the result of the computation. That, in a nutshell, is how FHE works.
Okay, so the locked box is a fantastic way to think about it, but what's the mathematical magic that actually makes it possible? What is really happening inside that box? So let's kind of peek under the hood and see what's actually making this whole thing tick. It all starts with a very particular kind of math.
So most modern FHE is built on something called lattice-based cryptography. I want you to picture a simple grid of points, like on graph paper. Now imagine stretching that grid into hundreds, even thousands of dimensions. It turns out that finding the shortest path between 2 points in one of these super high-dimensional grids is an incredibly difficult math problem. So difficult, in fact, that it's widely believed that even a powerful quantum computer wouldn't be able to solve it. And that gives FHE this huge advantage. It's what we call quantum resistant. So how does that actually give us security? Well, it comes from a puzzle called learning with errors. On the left here, we've got a really simple problem. If I give you A and B, finding the secret S is, well, it's basic algebra, right? But now look at the right. What happens if we add just a tiny random amount of noise or error into that equation? Well, that simple problem just became impossibly hard to solve. That little bit of intentional static is the entire foundation of FHE security. And you gotta understand, this noise isn't a bug, it's the whole point. It's the security feature. It's like cryptographic static that fuzzes the data just enough to keep it secure. But, and this is a big but, there's a catch. Every single time you do a computation on the encrypted data, like an addition or a multiplication, that noise level grows. And if you do too many operations, the noise can actually grow so large that it drowns out the original message and you can't decrypt it anymore. For years, this was the massive roadblock that made FHE seem totally impossible. And this is where the real genius comes in. In 2009, a cryptographer named Craig Gentry figured out how to solve the noise problem with this incredible idea called bootstrapping. It's this really ingenious, kind of recursive trick. The server takes a noisy piece of encrypted data, and it basically uses an encrypted version of the key to run the decryption process on itself homomorphically. The output isn't the original data, but a brand new, fresh, encrypted version of that same data, with all the noise wiped clean. It's literally like recharging a battery, letting you run calculations forever. What made Gentry's discovery so incredible was that cryptographers had been chasing this idea for over 30 years. You can see here it was first proposed way back in 1978. And for the next 3 decades, researchers kept coming up with partial solutions. They'd come up with systems that could handle, say, only addition on encrypted data, or only multiplication. but never both at the same time. It wasn't until Gentry's 2009 breakthrough, combining lattices and this idea of bootstrapping, that the dream of fully homomorphic encryption finally became real. So, ever since that breakthrough, the whole field has just exploded. And what we've learned is that it's not a one-size-fits-all solution. It's much more like a specialized toolbox with different tools that are specifically engineered for different kinds of jobs. So, if we look at this table, you can see some of the main tools in that box. If you're doing something that needs to be perfectly exact with whole numbers, think financial records or secure voting, you'd probably reach for a scheme like BFE. If your system is all about Boolean logic, like a private smart contract, then something like TFHE is a great choice. And for the world of AI and machine learning, which works with approximate real numbers, the CKKS scheme is pretty much the go-to. The main takeaway here is you have to pick the right tool for the job. And the problems we can start to solve with these tools, well, they're truly transformative. I mean, think about it. A cloud where the provider literally cannot see your data. Training AI models on sensitive medical records from a dozen different hospitals without anyone's personal info ever being exposed. Creating truly confidential transactions on a blockchain. You could even have competing banks collaborate to find massive fraud rings by running analysis on their combined encrypted data. And look, this isn't just some far-off academic theory. These ideas are already in use. At a massive scale, Apple, for instance, actually uses a form of this today. When your phone needs to fetch a logo for an email, your device sends an encrypted request. Apple's server can find and send back the correct logo without ever knowing what website you are actually asking about. That is privacy by design, happening right now. Okay, so there is, of course, one massive hurdle we still have to talk about: speed. Doing math on encrypted data is computationally, well, it's very, very expensive. Right now, a single calculation in FHE can be, and I'm not exaggerating, hundreds of thousands of times slower than doing it on regular, unencrypted data. This performance overhead is the biggest barrier to seeing it used everywhere. And the key to solving this is probably going to be specialized hardware, new chips built specifically to accelerate FHE. So when you boil it all down, what FHE does is it changes privacy from something you have to trust a company to uphold to a mathematical guarantee you can actually prove. It completely re-architects the way we interact with our own data. And that really leaves us with one final, very big question. If we could build a digital world where privacy wasn't just a policy, but an unbreakable mathematical foundation, what amazing new things would we build?